Hello, my name is Steve Miller. I'm a math professor at Williams College. I have my TAs with me as always. This time I actually remember to include my email address and a link to all the other talks. It's a pleasure to thank the Journal of Number Theory and Teachers as Scholars for support. And we're going to continue our probability lectures. We're going to talk about some advanced bridge hands and some poker hands. So here we have a 2 pair, 2 aces and 2 kings. And here we have all hearts. And so the question we want to ask is, what are the probabilities of certain events? So this slide should look very familiar. This is the review slide about what NCR means, N choose R. So we use C for combinations, and we either write it as NCR or with parentheses N over R. And it is the number of ways to choose R objects from N when order matters. So N factorial divided by R factorial, N minus R factorial. So for example, if we have 5 people and we want to choose 2 of them, 5 choose 2 is 10. So we give the people the same boring names. Maybe we'll eventually change this, A, B, C, D, E. There are 5 ways to choose the first person, 4 ways to choose the second, or 20 ways to choose an ordered pair. We remove the ordering by dividing by 2 factorial, because there's 2 factorial ways of ordering 2 people. What if we had 3 people? How many ways could we do it? How many ways could we order 3 people?
6, 7,
which is 3 factorial. Excellent. So here's a game. It's a modified version of two-handed bridge. So let's say hearts are trump. We're going to go through the deck looking at the cards 2 at a time, and you get to choose which card you want. So you choose one card and you dump the other. Now there's 52 cards in the deck. So if you do this, how many cards will you have in your hand?
13.
26. So it's a little bit more than the normal 13. We'll let you have 26
what
cards.
was it?
All right, it's double. We want to know, what is the probability that you can end up with all 13 hearts? So here, if your first 2 cards are the 5 of diamonds and 2 of diamonds, does it matter which one you keep? What about,
well, I would keep the 5
right. But over here, does it matter? No. What about the 5 of hearts?
Yeah.
Take the heart. 3 of hearts, king of clubs. Yeah, take the heart. Doesn't matter, take the heart. Okay, so here's the question. Is it possible to end up with all the hearts? Yeah. What is the probability you do that? And what could prevent you from being able to have all 13 hearts? So I'm going to pause and let you think about it. Okay, welcome back. And so, of course, the issue is, what if you had 2 hearts in one of the pairs? Then you can't choose both of them, and so that would prevent you. So that's the only thing that can stop you from getting all the hearts. So the quick.
Having 2 no hearts.
Yeah, but that doesn't hurt you.
Yeah.
It just means that pair doesn't help you get to your goal. It does take up space. So we just need to make sure we never have 2 hearts in the same pair. So I broke it up and I used these little boxes to represent the cards, and we don't know what they are. And so I'm not drawing all 26 pairs. That would make things too small. And here's how it's going to go. We have to choose some number of the 26 pairs to have exactly 1 heart. So maybe I chose the first pair, the 4th, the 5th, the 7th, and so on. In each pair, we have some number of choices of where to place the heart, in either the first spot or the second spot. And so I shaded it maybe where the heart goes. And then we have to order the 13 hearts in these spots. And then we have to order the remaining 39 cards. And then we have to divide by the number of ways to place the 52 cards. And so I put in a lot of placeholder question marks. So I want you to go through and pause this now and try to figure out what these are. So for instance, how many ways can you choose some number of the pairs to have exactly 1 heart, and so on and so on. So I'm going to pause it now and let you think. All right, so I am back from talking with my TAs, and what they said is, well, we have to choose 13 of the 26 pairs to have exactly 1 heart, because there are 13 hearts. In each pair, you have 2 choices. The heart could be the first card or the second card. Because we're doing this in an ordered way, we now put the 13 hearts in the 13 spots that are marked. There are 13 factorial ways to do that. We have 39 cards left over in 39 spots. There are 39 factorial ways to place them. And then how many ways are there to place the 52 cards? Since we're doing it with order mattering, it's 52 factorial. And so if we look at it, it's 26 choose 13 for choosing the 13 pairs of the 26, times 2 to the 13, choosing the spots, times 13 factorial for arranging the hearts, times 39 factorial, and then that should be divided by 52 factorial, and we get approximately 13.4%. And so what I did is I wrote a little computer program to test this and see how accurately it does. I wrote a computer program to test to see if the 13.4 was reasonable. And what I did is I made a very strange deck of cards. The first 13 values in the deck are just the number 1, and then the remaining 39 values is 0. And the reason is the 1 is going to stand for a heart, the 0 is a non-heart. And what I do is I'm going to choose my hand, and as long as the hand that I choose at the end, I'm choosing 1 card from each, as long as it sums to 13, it means I got all the 13 hearts. And so there's some nice ways of doing this. So what I'm doing here is I'm looking at the product of the 2 values in each pair. If the product is 1, it means I had 2 hearts in a pair and I lose. So as long as the product in pairs is never 1, I never have 2 hearts together. It's just a very efficient way to code. And I ran it 1,000, 10,000, 100,000, a million, 10 million times. And you can see the percent is pretty close to the 13.41. I'm getting 13.42. Okay. And so over here, just a little bit of a comment about the code, which I just mentioned. This is just to make it more efficient. Do I really care what the value is of a card if it's not a heart?
No.
And for a card, do I care only is it a heart or non-heart? Yeah, that's why I can write such a simple code. I don't need to keep track of other things. Now, if I was looking at other bridge problems, I would need to know other things about the cards. What suit are they? What value are they? But when you're doing problems, you have this choice you need to make. Do you write a more general program, which you can then use for other things in the future? Or do you have a problem and you say, well, I only care about solving this. I'm going to write a code that's tailored just to this. All right. So there's other versions of this game you can do. What if you look at the cards 4 at a time and you choose 1 each time? It is just barely possible to get all 13 hearts. But is it going to be easy or hard?
Hard.
Hard. If you have even 1 pair of 4 where you have 2 hearts, you're dead. What if you choose 1 out of every 6 cards? Is it possible?
There was 1 out of every 4.
So 1 out of every 4 was just barely doable.
Oh, no, it's not at all possible.
Yeah.
Because if you choose 1 out of every 4, you're going to get 13 cards.
Right, and if we choose 1 out of every 6,
you're just,
right.
you're not going to even have 13.
Correct. So we know that there's no way to do it if you choose 1 out of every 6 cards. So it's a nice problem. Try to figure out what is the probability you can do it if you look at every cards 4 at a time. All right. So what I want to do is the last thing for today is I want to talk about a poker problem. I want to talk about having a hand with at least 2 aces and at least 2 kings. How can you do this? What hands work? What is the difficulty? So I'm going to pause and let you think about it.
Well, then if...
Okay, so my TAs have said that there are 3 possibilities. 3 aces and 2 kings, 2 aces and 3 kings, and 2 aces, 2 kings, and some garbage card. So the challenge is we could have 3 of a kind and a pair. We have to be careful not to double count. So we want to try to figure out what are the probabilities of each of these configurations. So how would you count how many ways there are to get 3 aces and 2 kings, 2 aces, 3 kings, 2 aces, 2 kings, and something that's not an ace or king? So I'm going to pause and let you do one. So my TAs have given me the answers. For the first one, I have to choose 3 aces from 4 cards. It's 4, choose 3. I choose 2 kings from 4, 4, choose 2. So there's 24 possibilities. For the second, I choose 2 aces and then 3 kings. So 4, choose 2 for the aces, 4, choose 3 for the kings. Instead of 4 times 6, so 6 times 4 is 24. The last one is the trickier one. And TAs told me, well, we have 2 ways to choose 2 aces from 4. That's 4, choose 2. We then have 2 ways to choose kings. 2 kings from 4, 4, choose 2. And it took us a while, but eventually we realized, well, since this card is not an ace and not a king, that means there's only 44 cards left to choose it from, and it's 4, choose 1. And that's 6 times 6 times 44, or 1,584. How many 5-card hands are there? Well, I have 52 cards and I choose 5, because for all of these, it doesn't matter the order in which you get them. So a little bit over 2.5 million, 2,598,960. So if we look at the probability, we add up 3 different cases, we divide by the total number, and we get about 0.0628%. So it's a low probability. All right, so now what we want to do, we want to look at another approach. What if we choose 2 aces, 2 kings, and then choose another card? We could write this as 4, choose 2 kings. I'm sorry, choose 2 aces from 4, times 4, choose 2 kings, and then there's 48 cards left. Let's just choose one of them. So you get 1,728. So the ratio is about 0.0664. It's a little bit higher. Which of these two approaches is right and reasonable? So in fact, one of the TAs had even suggested that this might be the right way to solve the problem initially. And here's the problem. The first approach is the one that I believe is right. We know at least one of these approaches is wrong because they give different answers. It's possible that they are both wrong, but at least one is wrong. The second approach actually triple counts some possibilities. The problem is, imagine we have 3 aces, and we initially choose 2 of them, and we choose 2 kings, and then over here we choose an ace. Maybe we choose the ace of spades, ace of hearts, and the ace of diamonds here. So that would count as 3 aces and 2 kings. But we could have switched the ace of spades and the ace of diamonds and had ace of hearts, ace of diamonds, ace of spades. And that's the same hand, but it's now counted twice. Or we could have traded the ace of spades with the ace of hearts and had, ace of diamonds and ace of hearts and had ace of spades, ace of diamonds here, and the ace of hearts over here. So the third ace could be in here, and this is what's leading to the triple counting. Let's look at it another way. The number of ways we can have 2 aces, 2 kings, and a card that's not an ace or a king is 1,584. This approach says there's 1,728. So if we look at the differences, 144 extra hands. We claim that we have to divide by 3 because if we have 3 of a kind, there's 3 ways to choose which is the ace that comes in here, or which is the king that comes in here. So 144 divided by 3 is 48. 48 is 24 plus 24, and that's precisely the 3 aces, 2 kings, 2 aces, 3 kings hands. So I wrote a computer program to test this. And this computer program was actually a little bit more complicated. Now, to make things a little bit easier, I made the deck, the first 4 cards are all 1s, the next 4 cards are all 10s, and then every other card is a 0. What are the only cards I care about right now?
The 1s and the 10s.
Right, and what does the 1 represent? The
Aces.
and the 10 represent?
Mm.
So if you have 3 aces and 2 kings, what's the sum of the values of the hand? I can't do this one.
22.
3 aces and 2 kings.
3 aces, so 23.
23. And then what if we have 3 kings and 2 aces?
32.
32. And what if we have 2 aces, 2 kings, and something else?
Oh, should I say?
Yep.
22.
So we looked at them, and so if the sum of our hand is either 22, 23, or 32, it's a success. And that's much easier than trying to see, do we have 2 aces, 2 kings, or something like that. So what I did is I ran 1,000, 10,000, 100,000, a million, and 10 million, and here's the probabilities. And at 10 million, the probability was about 0.0649. Well, one method says 0.0628, the other's 0.0664. Where does 0.0649 fall? Right in between. Does this provide you any evidence as to which one is right?
Both?
Yeah. So what I did is I ran it a little bit further. Now, we need to go up to 100 million hands for this. Now, it took 20 seconds to do a million. How many seconds do you think it would take to do 10 million? So if it did 20 seconds to do a million, so how many more to do 10 million? If it's 20 seconds to do a million, 200 seconds. And how many seconds would it take to do 100 million?
2,000. 2,000.
And so it took 21.46 seconds to do a million, 2,157 seconds to do 100 million. It scales almost perfectly. And when we did 100 million, we got 0.0626, which is really close to the 0.0628. But the convergence here is so small, and the reason is the probabilities are so small, and they're so close to each other, it's hard for us to see the difference. All right, so probably the next one we will stop doing all these different bridge hands, and we'll do some advanced combinatorics next time. But as always, I hope you enjoyed the lectures. Be sensible. Have a